Okay. All right. Now every chapter has only the per unit system has a direct connection with the other chapter. We can discuss chapter 7 without discussing, for example, chapter 5. Okay. So these are standalone chapters. But anyhow, we will discuss chapter 7, and then that will be continuous actually. So to give you a relief from power flow, we used to in the lab you have so many labs on power flow. So that's power flow. So we will not repeat ourselves on this one. Okay. So symmetrical faults. We took some information about this in the lab. About what? About this. What is this? This is chapter 7, you mean, or chapter 6? About this chapter. Again, this chapter. Okay, chapter 7. Good, thank you. Yes. Okay, so that's good also. Of course, you will have this. So this kind of also the theory part of it. You understand it. Now, what I would like you to focus on is the building Y bus. We already discussed how to build Y bus when we discussed actually the nodal analysis. We discussed nodal analysis, and we measured that we found the diagonal and off diagonal matrices. The off diagonal is always negative. We put negative on the off diagonal, and the diagonal is the summation of all the lines which are connected, or the admittances which are connected to the bus. So if we have 9 bus system, this will be 9 by 9. So 81 elements. And then we will do what? We will do fault calculation. How we do it? Then we solve it by the bus impedance. Now this is called the bus impedance, which is the inversion of the Y impedance. So this is Z bus is used for fault calculations. Y bus is used for load flow. Okay, so it's simple. Now we have the load flow, so we know the Y bus, and then we will just invert it. Y bus is symmetrical matrix. If you invert a matrix, a symmetrical matrix, you will also get a symmetric matrix. So Z bus is also a symmetric matrix. Y bus, most of the elements in the power system are zeros. So we call sparse matrix. Most of it. Why? Because maybe bus number 5 is not connected to bus number 20. So 0 will be at the element. So Y520 will be 0. But when you invert it, Z bus is not necessary, will be zeros. It's not necessary to be sparse. Okay, so it will be different. Okay, the inversion of a sparse matrix will not give you sparse matrix. But for a symmetric matrix, will give you symmetric matrix. Okay, so using the bus, and then we have also the superposition. And we have the superposition tajmir. Okay, by opposing 2 voltage sources. So we do it by opposing 2 voltage sources. Okay, so this is what. Now, to do this, we need to simplify. Always as an engineer, you need to simplify the problem. Then you can work it, and then you feed the computer there for a very huge system. So sometimes that's what you will do. So now, and this are practical simplification, by the way, valid simplification. Transmission lines are represented by their series reactance. Okay, and the transformers are represented by their leakage reactance. So that is X and R at the series. Okay, there's no shunt. Winding resistance, shunt admittance, phase shifts are neglected, and that's okay, no problem. So synchronous machines represented as a constant voltage and direct with the subtransient reactance. Okay, voltage with subtransient reactance. Induction, can you hear the doctor? You cannot? How come? Yes, you can. Induction motors are ignored. Okay. Induction motors are ignored or treated as synchronous machines. So if there's an induction motor, then we treat it as a synchronous machines. Any other loads, non-spinning loads, that is not a generator, not a motor, we ignore it, because compared to this one will be small. Any non-spinning loads are ignored. These are the simplifications, network faults analysis simplifications. Now, why? Of course, you are familiar now with healthy, for example, health. I guess I shared another one. Healthy state. Healthy state, the current is at steady state. When there is a fault occurs, the current, you see now how much the current, 20 times, 10 times, whatever. It becomes very huge current at the beginning there, and then decays. So this is the part here we call subtransient state. And this is the worst. The current is very high at the subtransient state. At the transient state is high, and then becomes normal here at normal operating. Okay, at back to normal. Okay, so the short circuit happens here. Therefore, this one. Now, why we have the subtransient? Because this is the worst one. This is called subtransient. This is called transient, and this is called the synchronous reactance. Synchronous reactance, what we use, we put it in load flow. It's large compared, much larger compared to subtransient reactance. Okay, or to transient reactance. So why we take the subtransient reactance? Because the current will be high. Why the current will be high? Because X, this one is small. X double prime, the subtransient is small. Therefore, the current is high. So this is the worst. So that's what we calculate. Simple single line diagram of a synchronous generator feeding a synchronous motor. So okay, so a generator given the nameplate on the generator are these 0.15 watts. This one. Who will tell me now? 0.15 is what, in ohm or per unit? Per unit or ohm? 0.15.
As no units is given, it's per unit.
Huh? 0.15 is per unit or ohm?
Per unit.
Okay, it's per unit. Okay, the transformer, we give the transformers or the machines in per unit. It depends on the base. Okay, the old base. So here the old base, without actually giving all these, the old base, etc., is what, 13.8. The transformer is also in per unit. Okay, we don't give the transformers in ohm, but the lines is given in ohm. So it depends on what. So then we need to convert. What's the base? We did not discuss the base. Okay. We did not discuss the base, but when we have it, so we can have this one, and then you convert it from the per unit, from the old per unit into new per unit. Okay. If it's given, but now if we choose the base case is 13.8. If 13.8 is chosen at this part here, you remember now we are not looking at this 13.8, we are looking at this one here. When we say the base, it's after the transformer or before the transformer. Zone, when we say the zone, not the generator or the load, okay? The base, you look at the transformer. So therefore the base is 13.8. And 13.8. So this will be here, what will be 1 per unit. 13.8 is for the generator. The generator is operating at 13.8. Now, that's what we see. Okay, but then it depends. It depends on what the generator is operating at, 5% above rated or below rated value. Okay. Anyhow, this 13.8. If the base is for 13.8, of course, this will be 138 automatically. The base will be 138. Okay. If the base here is changing, of course, this will change. But now the base is 13.8. How do we know? This given. Okay. 13. So we started with the base. You start only in one zone. Okay. So therefore 13.8, then you will get 13.8, 138.8. This here also is 138.8. Oh, wonderful. So there is nothing to do. If this 13.8, then you don't need to do the old, the new, etc. Okay. Then this also will be 138, and this will be 13.8, of course. So the base as given with the rated values. Therefore, because the base is given, therefore x here will be the same. X here will be the same. We will not change it. And x here will be the same at the base, because it's given at the base, this base, the 13.8 here, and the base is 13.8. Therefore, all x's will be the same. And also this one here will be in per unit, of course, will be the same. And remember now, this is subtransient reactance. And you know why we do subtransient reactance? Because the subtransient reactance is much smaller than the transient. So we want to model the system. So we want the current to be high, the worst state. Okay, here, talking about this, the high current. If you do transient reactance, you will get this much current. So we want the worst one. Always when you calculate based on the worst. Then you set the circuit breakers, etc. The protection. Always the protection is at the worst. Always when you calculate at the worst. Okay, so to be at the safe side. Okay, to be at the safe side, then you install your breakers. These. Okay. Now, how to solve this problem here? Tamim, tfadal. Okay, go ahead. Yes.
So yes, the question is since the x double prime, 0.15 and 0.20 are the subtransient reactances. What about the x? Is it just for the transformer? So we're not looking at the transient or subtransient of the transformer itself.
Very good, very good, very good. There is no subtransient in transformers. Subtransient comes only from spinning. The transformer, there is nothing spinning on the transformer. Okay, good question here. When you do subtransient, you only do it for spinning a load, a machine. But the transformer, there's no subtransient. It's just X. Okay. All right. Okay, so what we do here, we model now. Okay, what is the problem here? The problem here indicates where is the problem. I decided maybe to take this out, and let me share maybe the other one that I put here. Okay, this is the one I would like to see. All right. Okay, so then you will just plug in the numbers here as after conversion to per unit, and we did convert it into per unit. Then I just plug in the number here. But remember now, this part here is voltage behind the reactance. So the reactance is 0.15, J 0.15. Why is J? Because it's X. Okay. So this is the model of a generator. A model of a generator is voltage or any synchronous machine. We model it with a voltage and subtransient reactance for the fault. If at steady state, we measure the voltage and X, direct axis, the reactance. Okay, steady state reactance. Here, because we're doing fault analysis, therefore, voltage and X. This is the generator. And then we go on to bus number 1. So we write 1. Then we go what for the transformer? Don't forget the transformer here is 0.1. So we put 0.1. Remember now, after we convert into per unit, because it's in this example here, the base is 13.8 and it works all the way that we don't need to modify any reactance. Okay. Then what you will do, the line now. The line here, we need to calculate the line. So we know now the line is V squared over S. So therefore we get this number. We convert the line into this base. This is the voltage. This is line to line, of course. We did not mention here line to line, but it's line to line, always in the 3-phase, and we already mentioned these. By default, it's line to line volt. Okay, so V square line to line over S, 3-phase. And this is line to line. So what's V square of the line is this part here. V square over S, they give you what? Give you the base. Give you the base. And then you will divide 20 ohm over the base, which is an ohm, of course. You will get this. And then what's held in here? So I will clean this one. Then what is this? 0.1. You will put 0.1. Very simple. You will go on 0.1 to X. And then this one here is 0.2. You will put 0.2, but this is a machine now, synchronous motor. Therefore, you will put a voltage. And so where, okay, and the reactance, subtransient reactance, 0.2. Now, where the fault happened at bus number 1. Remember now, at the 3-phase fault, this is easy. This is the part here. The fault happens at the bus. Now, the worst fault which happens at the bus, that the line has no problem actually. The line and the protection, so we can maybe use another line if there's a, but at the bus where all the lines come in. So that's the worst one, that when the fault happens at the bus. So the fault happens at the bus. So at bus number 1, we have what? Like a switch. Okay, switch. So the fault happens like this. All the here like this. So it's like this. So we just add all these 0.1 plus 0.105 plus 0.1 at one side, 0.15 on the other side. And these are the voltage. Okay, so the fault happens, when we say fault, it means to ground, all the way to ground, like this. So this is the circuit now, becomes a circuit, simple circuit. You have voltage, and you have. So what do we want to find? We want to find the currents. So to find the currents, we use the superposition. So this is one method to use the superposition. Other method is we use the Thevenin equivalent. Okay, the Z bus. Okay, so this is 0.15, and so what we do here, we have of course this one and this one. So we model the fault like this, opposite to each other. So if they cancel, you see the positive is down, here the positive is up. So they cancel. Why? Because at the fault, the voltage is 0. Okay. So they cancel each other. So we did not do anything here. We just make it 0, but we change it. Therefore, what we can do, if we have it, if we draw this at the positive down, then we need to add this part here. Okay, so this we call superposition. We call it superposition. We call it I double prime F, and this is F1, and this will be I double prime F2. So we add I double prime F1 plus I double prime F2. I double prime is the subtransient current, the fault current. Okay, so that's why we model this as two, because we want to divide them like this. We want to divide them like this. Yes. Yeah, Muhammad. Allah. Fadl. Nothing. All right. Then what we have here, so we can just model them, model these two. Okay, so we add these two. Now, so this is application of superposition. So we can add them, or we do it like this, as we mentioned there. Now, this is set equal to pre-fault voltage at fault. So we can have it, what we do here, we set this at the pre-fault voltage. Pre-fault voltage. And the positive is down. Why? Because the current comes like this, down. And the current also comes this, down. Remember, in here, in this part here, when we have a fault in here happens, to ground, current flows from the machine all the way to ground. The opposite now, the current flows from the machine, and also it flows from the generator to ground. It's like a sink. The fault is like sink, the sink. الماء, sink. Okay, بلاعة. The water will come to the sink, and the water also will come to this. So the current supposed to flow the other way. Actually, the current at steady state flows like this, going from the generator to the motor. But then, when there's a sink, the current now flows backward. Okay, and this is the still current of all the currents come to the sink, which is the motor. All right, so just 1 minute left. So simple, for simplicity, what you will do, these are before the fault, all before the fault, and this is after the fault point. I'm talking about the fault, but this is bus number 1. And this is before the fault. What before? Before the point, which is 0.15. And this is after the point. This is the point where the fault happens. That's the idea. The whole idea is very simple. So please don't miss this kind of problems at the exam. Okay? So what you're going to do to solve it, because you will be given a problem like this in the final exam. Okay? So I will leave, inshallah, to the next lecture, and then we will finish this, inshallah, in the next lecture. Any question you want to ask? Any question?
Yes, Doctor, please. I was in the lecture from the beginning, but I lose the connection in the middle, and you take the attendance. So please, can you put me as attend?
Okay, you're right. Yes, you're right. Yes. So then I can. Right, yes. But maybe you did not hear me, so you are not there. You joined that they are late. Okay, thank you all. Okay. So right, yes. Okay, you can hear me. Yes, tell me.
Yes, Doctor. I was here since 9:55, and we were disconnected at around 10. Then we tried to log in, but the blackboard wasn't responding until 10.
Okay, now the blackboard is okay. So please now register again for all of you. Please register again. Otherwise, we cannot. Okay, so I open it now for you. Just a second here. So please register, and then you can leave. For those who can hear me, please register. Okay, now it's open. Okay, the registration is open now. So please register. If you can hear me, please register. If you cannot, it means you are not around. Okay, so please register now for attendance. Thank you.